Hi students, we now move forward with the problems on design of clutches. We have already solved three problems on single plate clutch, and now we start off with designing of multi-disc or multi-plate clutches. So I will be solving at least the three problems on a multi-disc. So let us move on to the problem statement in the next slide. Okay, so a multi-disc clutch, I think before we look into the problem statement, we will review the functioning of a multi-disc clutch so you will be able to understand the problem statement much better. You would have seen this figure in the introductory video when we spoke about how a multi-disc clutch works. Okay, so let's review it again. So if you will closely look into this figure, you have a driving shaft which as we know will be fixed to the flywheel which will receive power from the say from the engine, and on the other side you have the driven shaft which will transmit motion and power to the uh, transmission system, right? So in between the driving shaft and the driven shaft we have a multi-disc clutch. So multi-disc clutch, as you can see, is made up of multiple plates or multiple discs. Okay. Now the discs that you see are categorized into disc A and disc B. Discs A are those which are connected to the driven shaft. There is a splined sleeve here, and disc A are connected to the driven shaft, and disc B that you see are connected to the drum, which in turn is fixed to the driving shaft. Okay, and this disc B are held in place by the bolts that you see here. Okay, bolts that passes through disc B and fixed onto the outer the drum. So when the driving shaft will turn, it will cause this drum to also turn, and since disc B are fixed onto the drum, they will also rotate. Okay, now when disc A, which are mounted on the driven shaft, when they are pressed against disc B, because of the friction, disc A will also turn, and since it is mounted on the driven shaft, the driven shaft will also uh, rotate. So that is how the power is transmitted. That is, power from the flywheel engine is transmitted onto the driving shaft, then to the disc B, and from disc B to disc A, and from disc A to the driven shaft. Okay. Now we use springs to exert that axial force needed to keep disc A and B pressed. Okay, for disc A to come in frictional contact with disc B, the axial force is important. All right, so this is how a multi-disc clutch works. Now, in your automobile, when you will press the clutch pedal, it will release this spring force, because of which disc A and disc B will no longer be in frictional contact, and the power and the motion will not be transmitted, right? And when you will release the clutch pedal, the spring force will exert, and both disc A and disc B will function as a single unit, and there will be transmission of power. Now another figure is shown here, which actually shows the multiple discs that we actually spoke about. In this figure, we see sets of disc A, three sets of disc A, and two sets of disc B. And you can see that there is frictional liners that are provided on both side of disk B, right? So this is how a multi-disk clutch will function, right? Now there is one important data here: 4 pairs of contacting surfaces. Now if you have now the total number of disks here is 1, 2, 3, 4, 5. Totally you have 5 disks, 3 of set A and 2 of set B. Now which how many surfaces are in frictional contact? You can actually see here, right? uh, 1 here, 2, 3 and 4. Therefore 4 pairs of surfaces are in frictional contact, all right, when you have a 5 set disk. All right, so okay, so with this like information, we will now move on to the problem statement of solve problem number 4 in the next slide. All right, so let's look into problem number 4. A multi-plate clutch made up of steel on bronze is to transmit 8 kilowatt power at 1440 rpm. The inner diameter of contact is 80 mm and the outer diameter of contact is 140 mm. The clutch operates in oil with expected coefficient of friction of 0.1. Allowable pressure is 0.35 megapascal. Assuming uniform wear theory, determine number one, number of steel and bronze plates, axial force required, actual maximum pressure, and average pressure. So this is the problem statement that we have, right? Now let's look a bit more closer into the problem statement. You see that the multi-plate clutch is made up of steel on bronze. What that means is uh, the set B, set B types of discs which you saw in the previous figure, which was mounted on the uh, driving shaft, are usually made up of steel. All right, and the disc or plates that are mounted on the driven shaft, that is set A, all right, is made up of bronze. All right, so why is this difference here? Because both the surfaces are supposed to be in friction, right? Therefore the coefficient of friction of the surfaces are very important, right? So that is the reason why we have different sets of materials or liners on the disc. Okay, now the multi-plate clutch is supposed to transmit 8 kilowatt power at 1440 rpm. The inner and outer diameters are known. Okay, and the coefficient of friction between steel and bronze in the presence of oil is mentioned as 0.1. Okay, now the allowable pressure that acts is 0.35 megapascal. Okay, and we know that 1 megapascal is equal to 1 newton per millimeter square. Okay, and they've asked us to assume uniform wear theory, right? And they've asked us to find out 4 factors. Number one, how many number of steel and bronze plates do we have or do we need, right? So that we need to determine. Axial force needed to keep the plates engaged to transmit this amount of power, and what is the actual maximum pressure and the average pressure between the discs. These are the 4 factors that we need to determine. Now we will look into the solution from the next slide onwards. All right, so you have the data here. We have already seen this. Outer the diameter is 140, inner is 80 mm, pressure is 0.35, RPM is 1440, coefficient of friction in the presence of oil is 0.1, and the power that needs to be transmitted is 8 kilowatt. Right? So let's look into the solution from the next slide onwards. All right, so let's begin with the first factor which they have asked us to find, which is number of plates. Right? They have asked us to determine how many number of plates are needed on the driven and on the driving shafts. All right. So, and they have asked us to make use of uniform wear theory. Okay. So now we will to find out the number of plates. We will, as usual, for uniform wear theory, we will find out the axial force. Okay. Now in our handbook we have the equation number 13.9d, which gives us the axial force based on the maximum pressure between the discs. Okay. Now the maximum pressure was given in the problem statement as 0.35 megapascal, right? So you know all the data that you need. Substitute that, and you will get the maximum axial force needed to keep the plates engaged, and that turns out to be 2638.94 newtons. Right now, once you know the axial force, then for uniform wear, you have the torque equation. Now, torque equation can be of two types. Since we know what is the power that needs to be transmitted, we can make use of the 2 pi nt by 60 formula and then calculate the torque. That is one way. Then we have also derived a formula for torque based on uniform wear uh, theory, right? So for we have two formulas for torque. Now let us begin by finding out torque based on the power that needs to be transmitted. You can find out T as 9.55 into 10 power 6 into power divided by RPM, which is nothing but power is equal to 2 pi nt by 60 into 1000. That same formula, when you will rearrange, you will get it in this form, right? Therefore, you solve this and you will get the torque as 53.05 into 10 power 3 Newton mm. So this is the torque. All right. Now this is the torque that we need to transmit 8 kilowatt power at 1440 RPM. Okay. Now let us use the uniform wear theory formula for torque that is given as 13.9 F in our design data handbook. All right. Now here you know that dmw is actually the mean diameter, which is the average of inside and outer diameters for uniform wear, right? So let's solve this now. Now, if you will find out the mean diameter for a 140 outer and 80 inner, you will get the mean as 110 mm, right? Now, torque we already know is 53.05 into 10 power 3. Therefore, T we know and all other factors except for N dash you know, right? Therefore, let us calculate N dash. What is like N dash? N dash we know is the number of contact surfaces or the number of pairs of friction surfaces. All right. Therefore, let's solve this, and when you solve for N dash, you will get it as 4. Okay, that is N dash is 3.655 or approximately 4 surfaces. Remember, N dash is not the number of plates. N dash is the number of surfaces, that number of pairs of surfaces in frictional contact. Right now, from the previous figure which you have seen, if you will observe that same figure, you will see that we add 4 frictional surfaces, right? 1, 2, 3, and 4, right? 4 pairs of surfaces which are in frictional contact. Now, for n dash equal to 4, therefore, you will need 3 discs of set A and 2 discs of set B. That is, on the uh, driving shaft you need 3 and on the driven shaft you need 2. All right. Therefore, you can actually say that uh, the total number of plates therefore is 1, 2, 3, 4, 5. Right. Therefore, if the number of surfaces in contact is 4, then the total number of plates will be n dash plus 1, right? So the number of plates will be 5. To obtain a uh, to obtain the number of frictional pairs as 4, right? Okay, therefore we will go to the next slide forward. We now see that we have obtained the number of frictional pairs as 4, and from the figure we see that Z1, which can be called as uh, pressure plates or the plates which are mounted on the driving shaft, is equal to 3, and Z2, which will be the uh, friction plates or the clutch plates which are mounted on the driving or the driven shaft, is 2. All right. Therefore, the total number of plates will be 5. Z1 plates on the driving shaft will be 3, and plates on the driven shaft will be 2. All right. Or the number of pairs of contacting surfaces n dash will be equal to Z1 plus Z2 minus 1. Right. That is 5 minus 1 is equal to 4. All right. Or we can say that we can rewrite this and say that the total number of plates n, which is equal to Z1 plus Z2, is equal to number of frictional contact surfaces plus 1, equal to 5. Right. Therefore the answer to the second part is also like obtained now. That is uh, n is equal to 5, Z1 equal to 3, and Z2 is equal to 2. All right. Therefore the number of plates is solved. Now moving on to the second factor which they have asked, it is the axial force. Right. Now they have asked us to assume uniform wear theory. Now we know that for uniform wear uh, theory, you can directly find out the axial force using the torque equation, right? Using the torque equation 13.9 F, you can rewrite it to solve for axial force FAW, right? Therefore, you can rewrite it. You know the value of the the torque here, and the mean diameter n dash also you know, frictional coefficient of friction also you know. Substitute and you will get the axial force as 2411.36 Newton, right? Therefore number of plates is obtained, axial force is obtained. Let's move into actual maximum pressure. Right now, since we are talking about uniform wear theory, pressure is not uniform across the plate, right? We know that the disc has slightly worn out, okay, and therefore the pressure is not uniform across the plate. And if you remember the introductory video, in the pressure distribution figure for uniform wear, we see that pressure is maximum at the inner diameter, and as we go outwards, pressure will fall, right? Therefore maximum pressure occurs at D1. All right. Now we have formula for uniform wear 13.9D, which gives us the axial force as equal to 1 by 2 pi P max di into do minus di. Right. Now in this formula here, axial force we know we have obtained it as 2411.36. You know all the other factors, but the maximum pressure P max. Solve for that. Solve for the maximum pressure and you will get it as 0.32 megapascal, which is the average, which is the maximum pressure. Right. Now the last factor which they have asked us to calculate is average pressure. Okay. Now average pressure also can be obtained from the same formula, but instead of maximum pressure, you substitute it as, sorry, instead of inner diameter di, we will substitute it with the mean diameter. Since we need average pressure, you will actually substitute average diameter here, right? And then you solve for the average pressure P. When you will solve for P, you will obtain it as 0.23 megapascal, right? Therefore, the maximum pressure is 0.32. Required pressure is 0.35 as was given in the problem statement. But the maximum pressure is 0.32 and the average pressure is 0.23 megapascal. All right, so with this we end with problem number 4. We will discuss problem number 5 in the next video.